I wanted to show you how to analyze amplifiers using Spice, LT Spice. You've probably heard me talking about how you can find the voltage transfer curve and some other information. So let's have a look on how to do some of these things in Spice. I had to put in this model. I'm using the Mac version of this, which is a little primitive, but everything's there. I'm doing a right click on the screen. I do that with 2 fingers and a click. And I'm going to go down and draft and pull down to where it says component. And then I type NMOS, and it shows us that there are 2 different NMOS models, and the one we want to use is the NMOS 4 model. It's got the substrate terminal, drain, source, and gate. And if you just put that in there, you can drop it in. I don't really need that. I'm going to escape, and then I will just delete this one, which I'm doing like that. So I've already put in this MOSFET. I'll warn you that you have to be real careful to get this substrate connection made. Sometimes it looks like it's done and it's not. I can test. I'm going to put the cursor next to it, do a right click, highlight that net, and I notice that the entire, everything that's tied to these ground terminals is lit up. So that's good. All right, make that go away. Apparently not. Well, I'm not going to worry about it. So I've also added labels to some of the nodes. I put in a resistor. I had to edit it to put in its value. I have an input signal, which I'm going to be sweeping in a DC sweep in just a second, and that'll give us the transfer curve. I had to put in this model for the NMOS. I had to tell it what the model is. The name of the model is NMOS 1. And it's given here. I just dropped it right on my schematic. All right, so I think we have everything we need to do to run this thing. I'm just going to click on run, and it's plotting the voltage transfer curve. Let me also plot I'm going to put my cursor over this thing, and if I can do it in just the right place, it'll turn into this funny little symbol there, which is a current measuring device. And it shows us here that when the input signal, which is what we're sweeping the horizontal axis with, from 0 to 5 in 20 millivolt steps, when the input is less than the threshold voltage of this transistor, we'll learn more about the transistors later, when the voltage at the input is less than 0.8 of a volt, it's in a region where it's basically off. Then the current rises, and then eventually when the current gets sufficiently large, the transistor enters a third region of operation where the current doesn't increase so much. When there's no current, the output voltage, there's no voltage drop across this drain resistor, and so the output is stuck at 5 volts. Once the current begins to come up, the output begins to drop as we have a voltage drop across this drain resistor. And eventually when the output gets lower, again, we go into a different region of operation, and the output voltage drops asymptotically towards 0. So we can now drop a cursor on this. I'm going to left click on this guy. It attaches a cursor to this thing. I can use it to read out the voltage horizontal, vertical as a function of horizontal. As I move this around, you'll see that the output voltage is stuck at +5 when there's no current. But as soon as current begins to flow, we see that the voltage begins to drop, and again, it asymptotically approaches 0. So if we just wanted to read off of this thing, the voltage at which the output is, say, about VDD over 2, VDD is our positive supply, it's 5 volts. At about 1.3 volts, this thing is about halfway between the 2 limits. I could attach another cursor. Let me click again, and I can just adjust this the 2 cursors around the operating point. And if I can adjust the horizontal axis so that the difference, delta X, is about close to 100 millivolts, we see that the delta Y is about minus 960, about 1 volt. So the gain of this thing is approximately, we can actually read it off of this slope, so it's about 9.8, 9.9 for this thing. And that's an estimate of the gain. close to the operating point. Just a quick and dirty way of estimating that. All right, so that's one way of finding the gain of the amplifier. Let's see now, we could also use transient analysis. I'm going to right-click into this thing. I'm going to right-click here, and it says, help me edit the analysis command, and it says all these different possibilities. So I'm going to change it to transient analysis. I'm using, well, let's decide what we want to do. I'll come back to that. Let me edit the voltage source, and then we'll decide what we're going to do. I want to do a sinusoid. We decided that 1.3 volts was a good bias voltage that would get the output sort of in the middle of the range. Let me put a fairly small input signal in here, like something like 0.05 volts, 50 millivolts, and let's choose a frequency in hertz of, say, 1 kilohertz. And I'll make that pop up on the schematic, close this, and there we see that we have the sine wave with its 1.3 volt offset, 50 millivolt amplitude, and a 1 kilohertz frequency. Now let's go back and edit this thing. I right-click, help me edit. It's just helpful to remember these things. Go into the transient command, and the signal that I put in was 1 kilohertz. 1 kilohertz signal, you have to think about this. 1 kilohertz signal has a 1 millisecond period, and so if we want to do 3 cycles of that, we can stop at, say, 3 milliseconds as our ending. There's a lot of other things we can put, but this is all we're going to need. And that just edits this command for me, and when I hit OK, it'll drop it right on the schematic. So I think we're ready to run this thing. Let's see what happens now. I run it here. It is plotting the output voltage, and that looks like a nice sinusoid. Let's see what the input was. I'll put this symbol on here that says I want to plot a different voltage. So the input signal is the one that was described by this, and it's 50 millivolts amplitude above and below 1.3. We notice as the input signal goes up, the output signal goes down. This is an inverting amplifier. We could get the gain off of this with a couple of cursors. Let me put the, we know the amplitude of the input. If I put a cursor, for example, at the top up here, and drop another cursor, there's just 2, drop it at the minimum, and look at the difference between the positive and the negative. It's about 2.85 volts, 1.85 volts, so it's about 200, about 1 volt peak to peak, and so it's 1 volt peak to peak. The peak to peak of our 50 millivolt peak amplitude signal, its peak to peak signal is twice that. So the point is, again, the gain is about 1 volt divided by 100 millivolts peak to peak in both cases. It looks like a pretty nice waveform. Let's see what happens if we put a bigger waveform in. So we're going over a bigger fraction of that input transfer curve. So I'm going to edit this guy. I can just edit the thing because I know what this stands for. And if I put in, say, 0.30 volts, just to pick a number, this is 0.3 of a volt. If I run the simulation now, for the bigger input signal, we see that the output is substantially distorted. So that's another way we could get the, now we wouldn't really want to talk about the gain so much because we're not just multiplying the input by a constant anymore. There's some other things we could do with this. Let's see. Let me close this one. Let me open a different version of this. Let me open Amplitude 2. I've already done some of these files. Here's another way we can do things. I edited the input source to include a DC value, which we need, and an AC amplitude of 1. And this is going to be what's called a small signal analysis. In this case, we're going to do .AC analysis, and we'll sweep the AC signal between, let's just show what this is all about. So we're sweeping this. We had a number of choices. We could sweep it linearly or logarithmically. 10 points in every decade, every factor of 10, and we'll put 10 points in every decade logarithmically from 100 kilohertz up to 10 gigahertz. Drop that one in there. We've got an AC input of 1. This is going to analyze a linearized version of this thing. We'll talk more about what that means. Don't worry too much about what it means, but it's going to be really important. And we can now simulate this, and we will find out how this amplifier's gain varies as a function of frequency. And what we find is that at low frequencies, it's 20 decibels, which turns out to be a linear gain of 10 volts per volt, which is what we expected. And then we can drop a cursor in here. And if I move the cursor around, the classic thing to do with this is to find the frequency at which the gain drops by 3 dB. So it was 20 dB at low frequencies. So when it gets to about 17 dB, I'm reading off down here, when it stops at about 17 dB, close enough, we read off the frequency and it's about 1.6 something gigahertz. So we would say that the bandwidth, the 3 dB bandwidth of this signal is about 1.6 gigahertz, which is pretty good bandwidth. It's caused by capacitances that are included inside the MOSFET. What else could we do? Let me do one more trick. I feel like I'm kind of on a roll here. Let me run a thing that I already ran. Let me see, I want to make sure I get the right one. Okay, here's a trick. I have included a step, a parameter. The parameter is the amplitude. I put it in curly brackets, and I used it to this variable now, which I'm going to sweep over a range, and I've used it to affect the amplitude. So if I go in and look at this thing, you see the thing that's doing the amplitude is a variable. And now I can sweep that variable over a range. I'm going to sweep it from 0.04 volts to 0.32 volts in 0.04 volt steps. And we'll just see what that plot looks like. And I'll just tell it that this is what I want to plot. And now we get a whole family of curves there showing how it starts out sinusoidal. As it gets bigger, the lower part gets almost clipped, really hitting a pretty hard maximum. And the upper part is just getting kind of scrunched more and more up towards the positive value. One other thing I was going to show you is how to understand the frequency components of the output. So here is another trick you can do in SPICE. So I made this into a comment. So if you look carefully, you'll notice I put a semicolon in the first line of this thing, and that turns it into a comment to SPICE. It says just ignore it. And I added a new thing that says set the parameter amplitude AMPL to 0.06. All right, and I put it then in here. So that's just a way of setting this to a particular value. So we're really just running one simulation. And then I'm going to ask it to do this dot Four analysis, and I'll show you what that does. I'm not really interested. Well, we'll go ahead and look at the waveform. So it looks kind of like a sine wave, pretty much like a sine wave. But we're going to now look at the frequency response to this. I'm going to right-click into this. I'm going to go View, SPICE Error Log, which I could have done Command-L. Control-L would have worked on a PC. And it shows me that I can get information about the new frequencies that has been generated. It tells the amplitudes of those new frequencies, and it tells the total amount of power that is in all these upper harmonics compared to the amplitude of the input. And that's called the total harmonic distortion. It's a measure of how sinusoidal this signal is. And 2.5, 2.6% is what we're getting. That's not great, but it's not too bad. We can do a lot better, as you'll see later. If we run a bigger signal into this thing, I'll just change this parameter to say, I don't know, 0.36. And we can run this thing again. We get this distorted sine wave. If we now look at the Fourier analysis of this thing, again, it'll tell us what frequencies make it up. And if you look at these numbers, I didn't really look at them carefully, but if you look at them, they are at multiples of the original input frequency. The original input frequency was 1 kilohertz. We have new components, and there's a substantial amount of power in these things, and the total amount of power in the higher harmonics is about 16%. That would be a very distorted sounding waveform. A sine wave sounds just like a pure tone. This would sound like more of a buzz sort of sound. So this gives you an idea of some of the things you can do with SPICE. We'll learn more how to use it and how to get these things. There's a lot of tricks to learn. but this will get you started. Again, you don't need to know a whole lot about amplifiers yet, but this is more or less just a preview. All right, well, we'll talk about this in class. See you later.